Hey, if you've ever stared at a page of vector calculus and just felt completely lost, you've come to the right place. We're going to tackle a classic topic from Elements of Electromagnetics, classifying vector fields, and we're going to cut right through all that mathematical fog. My goal here is to give you a crystal clear guide to sources, sinks, and swirls.
I mean, seriously, if you're an engineering student, I bet you've stared at a page full of these symbols, gradient, divergence, curl, and just thought, what is the point of all this vector calculus soup? It all feels so abstract, and believe me, you are definitely not alone.
But here's my promise to you. There's a simple, way more intuitive way to think about all this. By the end of this explainer, you're going to have a foolproof two-question test that lets you classify any vector field that comes your way. So, let's do this.
Okay, so to build our test, we first need to stop thinking about these things as just, equations on a page. We need to start thinking about them as descriptions of how things actually behave in the real world. And it all boils down to two really simple ideas: sources and swirls. First up, divergence. You'll see it written as del.A. At its heart, divergence is just a measure of how much a field is flowing out of a single point. You can think of it as like a source meter. Is stuff exploding outwards from this point, or is it all rushing inwards?
The perfect way to picture this: a sprinkler head. It's shooting water out in all directions, right? That spot has positive divergence. We call that a source. Now picture the drain in your bathtub. All the water is flowing into that point. That's negative divergence, and we call that a sink. It really is that simple. Outward flow is a source, inward flow is a sink.
Okay, so if divergence is all about straight line flow, out or in, our second concept, curl, is all about rotation. As the name kind of gives away, curl, which we write as del cross A, it measures the swirliness of a field at a specific point. And here's the best way to visualize it. Imagine you have this tiny imaginary little paddle wheel, and you drop it into a river. If that little paddle wheel starts spinning around in place, then boom, the field has curl, right there. But if it just gets pushed downstream without rotating at all, then there's zero curl. See? It's super intuitive. All right, so now that we've got a good feel for sources and swirls, we're ready for the two golden rules of vector calculus. These are fundamental truths. I mean, think of them like unbreakable laws of physics for how fields work, and they're the entire foundation for our classification system. And we're not just pulling these out of thin air. We can find them right here in the source material. Appendix A10 of the textbook lays out a bunch of these vector identities, and the first one we need tells us something really deep about fields that have that swirlingness.
And here it is. The divergence of the curl of any vector field is always, and I mean always, zero. Del cross A is always zero. This isn't just some neat math trick. It's a fundamental truth about how vector fields are built. So let's translate that back to our simple sprinkler and drain language. What this means is that something that is purely a swirl cannot also be a source or a sink. It makes sense, right? If water is just spinning in a perfect whirlpool, there's no net flow outward or inward from the center. And by the way, a field with zero divergence has a special name. We call it solenoidal. It's source-free.
All right, let's head back to that textbook appendix for our second golden rule. This one is about a special kind of field that comes from something called a scalar potential. Think of things like a temperature map or a pressure map. This rule states that the curl of the gradient of any scalar field is, you guessed it, identically zero. Del cross del V is always zero. This is such an important idea. It's even called out as a key concept in review question 3.6 of the textbook.
So what does this mean in plain English? Well, a gradient field always points in the direction of the steepest change. Think of a ball on a hilly landscape. It's always going to roll straight down the steepest path. It's not going to just spontaneously start swirling in a circle. So a field that comes from a potential like this has no swirl. We call this irrotational or sometimes conservative. Okay, quick recap. Golden rule 1, if it's all swirl, it can't have a source. Golden rule 2, if it comes from a potential, it can't have any swirl. These two facts give us everything we need to create our super simple, super powerful two-question test to classify any vector field. And here it is. It's just a two-step checklist. For any vector field you're given, you just ask. Question 1, does it have sources? And to find out, you calculate its divergence. Is del.A 0? And then question 2, does it have swirls? And to find out, you calculate its curl. Is del cross A 0? The answers to just these two questions tell you everything you need to know.
Okay, enough theory.
let's put this thing into practice with an example straight from the textbook. This is from review question 3.7. Now we're given this vector field A. I know it looks a little intimidating, but our two-question test is going to make this easy.
So question 1, does it have sources? We're going to find out by calculating the divergence. So we take the partial derivative of the x component with respect to x plus the partial derivative of the y component with respect to y plus the partial derivative of the z component with respect to z. And when we add all those up, we get our answer. And the result is 6xyz minus 2. Now, is that expression always 0? No way! So the divergence is non-zero. And that's our first answer. Yep, this field has sources or sinks. It is not solenoidal. On to question 2, does it have any swirl? We've got to calculate the curl. Now this involves working out that big matrix determinant with all the partial derivatives. But when you actually work through the math, just look what happens. The x component is x cubed minus x cubed. The y component is 3x squared y minus 3x squared y. You can see where this is going. And bam, every single term cancels out perfectly. The curl of this field is the 0 vector. So we have our second answer. Nope, this field has no swirl. It is irrotational, which also means it's what we call a conservative field. So our final classification, this field has sources, but it has no swirl. Okay, now this is super important because this is a trap that a lot of people fall into. It's really common to think that a field has to be either solenoidal or irrotational, like it's a one or the other choice. But that's just not true. These two properties are totally independent. A field can be both, or it can be neither. This little chart lays out all 4 possibilities from our two-question test. If both the divergence and the curl are 0, the field is both solenoidal and irrotational. If only the divergence is 0, it's just solenoidal. Our example problem fell into this third category. It was irrotational only. And finally, if both tests give you a non-zero answer, well, the field is neither.
So the huge takeaway here is this. Any vector field, no matter how complicated and messy it looks, can be totally understood by just asking 2 simple questions. Does it have sources and does it have swirls? Which kind of leads us to one last really interesting question. What about that fourth case? What does it even mean for a field to have both sources and swirls? Well, it turns out that any field can actually be broken down into the sum of a source-free part and a swirl-free part. This is the whole idea behind the Helmholtz decomposition theorem, which is a massive cornerstone of electromagnetism. But that is a topic for another day.